my son wanted to be sure. He was very disappointed he couldn't come on the trip, so he wanted a friend to come with me. So we got an unnamed giraffe friend. I'm really excited that I can be here today. I've had to get used to giving talks to people who don't know anything about Haskell, and now I find myself more comfortable in that position, and so bear with me. I've been working for a while on using hardware transactions to speed things up, and specifically we'll look at software transactional memory and Haskell. I'll start by sort of describing what transactional memory is from the perspective of the transactional memory research community, and how that connects to the STM and Haskell, and then look at some of the implementations that I've done of hardware transactions and how well those perform, and there's a story to how I've kind of made progress in this, and how that relates to characteristics of GHC. So what is transactional memory? From the research community in transactional memory, it's really these two ideas, and they play off of each other in a really nice way. So first, you have to be able to express things that are atomic without saying how you're going to get that atomicity. And the other is, in your underlying implementation, we're going to be optimistic and do the speculative execution, where we assume things are going to work out, and then verify that they do, but always be able to kind of go back to some safe place. So implementation-wise, it's these two themes that transactional memory plays off of. Haskell does an excellent job of expressing this atomicity much better than you can do without going through a lot of hoops in other languages, and that's really great. It's part of the reason why there's lots of users of STM in Haskell. So under the hood, the STM monad, when it's executing, is going to do reads and writes to transactional variables. And we're going to track those reads and writes, not actually perform them, but we're going to track them in the transactional record. And well, if you do a read that you've already written to, you'll see that read out of the record, but we don't actually touch any of the mutable state until we get to the end, but we make this assumption that things are going to work out. So then we have to validate that assumption held. So we check to see, is the state of the world the state that we expected for this transaction to commit? So there's the validation and the commit that actually performs the update. And if the validation fails, we just start over. And in this sort of scheme, we don't have to do a lot of work to start over. We just throw away our transactional record and keep going. Please interrupt me if you have any questions about how this works. So there's two implementations of this in GHC. The coarse grain lock version, which is actually slightly bit rotted right now. I need to send some patches to fix that. But the idea is you run this whole speculative execution with the transactional record, but then when you get down to that part where you're going to do the validation and the writes, you take a global lock. And that means that all of the transactions that are in the system that are trying to commit, they all commit one by one. So they do that last little bit serially. And that ensures that that there aren't conflicts on the commit. And there's, state of the art has moved on for this sort of style to things like the no-rec algorithm. The other implementation is the fine-grained locking one, and this is complicated. Each TVAR now has a lock, and there's this two-phase commit. Very easy for things to go wrong. You have to really reason about it to get the implementation right, and there were bugs, and we've fixed some of them. There's still bugs on ARM, which it occurs to me the really easy route is just to switch to the coarse grain. So for ARM. So, so what's hardware transactional memory? Well, the original transactional memory idea was, let's have hardware support for this. And now that finally has been realized, and we have machines from IBM and Intel that have hardware transactional memory support. Generally, what they do is they sort of punt on the hard problem, and they just solve the easiest possible hardware transactional memory problem they can. And so you still have to have this software fallback of some sort. So in particular, the Intel implementation is targeted at replacing global locks in existing programs. So if you have some sort of critical section and you're doing some work in it, instead of actually taking the lock, you just say, this is a hardware transaction and this is the lock that would normally protect this. And it starts running speculatively, and all of the action that goes on in the L1, we don't publish that information from the cache out to the other cores. We kind of keep it secret. And that's like the transactional record. Your L1 cache now becomes your transactional record, and you can throw it away by just invalidating your cache, or you can commit it using some special in the hardware ability to commit a lot of cache lines. So the performance of this is really predicated on staying in the L1 and having good L1 performance. And those are both good things for high performance, regardless of whether you're using transactional memory or not. So it's a really good story for Intel. So my work takes the existing STM implementations and applies these hardware transactional memory support to speed that up. So the obvious, very easy way to do this is to take the coarse grain STM and instead of taking the global lock, run that critical section in a hardware transaction. If it fails due to a conflict, well, we may try again, or you could inside that critical section see a write that happened, and then you say, oh, we failed to validate. Then you start over the software transaction. But hopefully you can do all of these commits in the hardware transactions, and when that happens internally in the machine, what happens now is none of the cores have to talk to each other about synchronizing that global lock. So the number of messages that are happening internally on the machine's bus drastically reduce. So that's where you're getting the performance benefit, is you're just really cutting the amount of communication that happens on inside the processor to sort of minimal amounts. But Haskell transactional memory has some other features that aren't really part of what the transactional memory community thinks of when they talk about it, but they're really crucial for the way that people use software transactional memory in Haskell. So that's the retry and or else features. So normally the transactional record is how we support this retry and or else feature, but which we can do at this level, but we want to go even further. So instead of just looking at that one critical section, what if we execute entire Haskell transactions, what follows after the atomically block in a hardware transaction? So if we do that, the hardware is tracking all of the writes, not just the writes to the TVARs. It doesn't know any sort of distinction. So we're somewhat at a disadvantage. We're tracking a lot more things transactionally than we need to. But we get the benefit of we don't actually need to track that transactional record at all. We can perform the writes directly to the transactional variables. But we run into a problem there, right? we have to support the retry mechanism, and so we need at least an approximation of the read set for the transaction. So we do that approximation with a Bloom filter instead of an exact watch list, which is how the fine grain, well, how both of them, how the existing SDM uses it. So we do a trade-off, and instead of being exact in our wake-ups, we're imprecise in the wake-ups, but that's okay. We just can't miss any wake-ups, which we don't. So some other work that we have to do, we have to lower the level of the implementation of the transactional memory runtime support. We really need this to get kind of baked into the code sites to avoid extra memory use. So when we're really just writing to a transactional variable directly, we really want the code to, on the hardware path, write directly to it and not have to kind of do a function call and then write and then come off a function call. When evaluating this, we can't even get to the point where we can distinguish the performance of having hardware transactions or not until we get rid of some things that really kill performance, like the standard pseudorandom number generator really is just not workable. It appears that things like using GIMP, the allocator in there, just doesn't perform well with hardware transactions. I haven't figured out all of the details, but by stripping away these things, we're also pointing out places where the GHC runtime is not doing as well as it should on sort of memory performance-wise. Because all of these are reflective of how well is this code running in terms of the L1 cache. And then this last thing is we really need the ability to express at the user level when they're writing their applications a more compact form of the data that they're working with. So I don't know exactly how to call it, what to call it, but mutable unboxed values is what I end up calling it. And expanding on that, oops. We have this picture here. So normally, if this is an example of a red-black tree node, each pointer in the node is going to point to a transactional variable, and then that variable is going to point to the heap object that's pointing to. And the mutation is only going to happen inside the TVAR. This extra level of indirection is going to be really costly because potentially each TVAR is going to cost us an extra cache line. And so that sort of per node, that doubles the memory footprint in terms of cache lines. And in a sense, that sort of halves your performance for your hardware transactions. So instead, we've added this sort of transactional struct here, where all of these, both pointers and values, are mutable. So the color moved from being an indirection, a pointer for that single bit, to a whole TVAR is now just a word field in this structure. So we use this by kind of duplicating the small array functionality and adding support for it in the STM and the HTM. So unfortunately, it turns out to be really ugly and unsafe to write this. So what I'm really hoping for is to be able to figure out a good story for getting this to the level where users can write this. And I think it's a pretty big design space, so I'm hoping to have some good conversations here about how we can address this side of things. But it's a rainy day and I'm a grad student, so this is good enough for now. So how's the performance? How fast can we go? We have a big machine which has been really enlightening for finding all kinds of unoptimal ways that the memory layout can be. And right now, most of our tests are on this micro benchmark on red-black trees, where we're just really quickly doing inserts and lookups and deletes. And so it's sort of a steady state. We want to see the throughput, how many transactions, concurrent transactions can we do. And here it is for 50,000 nodes on average. And there's a lot of different variants here, so we'll walk through one by one, but you can see the orange line on the top there. That's sort of the best hybrid implementation that I have. And if we scale it down a bit to 5,000 nodes on average, we can do a little bit better distinguishing of what's going on. So I'll walk through each particular curve here. So this is the STM as is, with the addition of hash map from unordered containers as sort of a reference. So sort of the feel that I get is if people are using STM for a concurrent data structure and they see it as a bottleneck, they turn to putting a hash map in an IO ref and using atomic modify IO ref. So that's what that blue curve is. And you can see you get the best performance out of that for small number of cores, which most people have machines with small number of cores, so that's still great advice. But you can see as you get a lot of cores, things drastically change. So the fine grain is really critical for getting good performance here. So here's, if we do that really simple thing with the hardware transaction for the commit, we see all of a sudden we get outstanding performance from the coarse grain lock version. And this is really awesome. Yeah.
Sorry, just quick clarifying question. The STM find here is what most people are running today in Haskell?
Yes, that's the default.
And it actually continues to scale pretty well. So.
Yeah, once you've removed things like the random number generator, that's bad.
Is that used by STM?
No, it's not used by the implementation, but I mean, it is if you're using like a concurrent skip list. So the one that's on Hackage, concurrent skip list, uses the standard number generator in a particularly bad way. I had a Google Summer of Code student this last summer that did some work on doing some new concurrent data structures for STM, and some of those I'm going to look to in the future to kind of update and get some more benchmarks. But yeah, that's not used inside that, but that's used in my benchmark to just say, let's do some random inserts and removals. So what this is telling us is Intel's new feature allows us to write code that's really easy to reason about with a single global lock and get the performance that's almost the same as this complicated fine-grained locking scheme. And that's a great story. So there are probably a lot of other places in the runtime system where we can do this sort of simple transformation and get some really good performance. I'm excited about exploring some of those. One potential thing that you could do is something like a with mvar that you say with mvar HTM or something that could turn what's a global lock in your program into one that often runs in a hardware transaction. So you could see some really cool ways to get good performance. So we can do the same thing with the fine grain, and now we are outperforming the original STM. So again, that's great. If I jump back here, you'll notice that we don't outperform the fine grain STM on the larger tree here. So that black dashed line is now below the red dashed line. And that's due to when we start to hit these memory limits, especially on this half of the graph, we're using hyperthreads, and that halves the amount of L1 cache that you have for each thread, because they're sharing the L1 cache once you're at that level. So anyway, we can really start to see the memory implications, and that's great. So the next is the hybrid version, where we're running the full Haskell transactions, and we see we get sort of mixed performance. It's a lot noisier also. It's hard to get good performance here because running the Haskell code really has strange and varying memory footprints as we're running. We can't be sure about a lot of alignment issues, a lot of sizing of things, and so this is sort of the interesting thing that I read out of this is the detrimental things to hardware transactions. They're amplifying things that are also detrimental for just normal execution. So improving some details about memory layout and the way that Haskell code executes or the code's generated, things that improve the hardware transaction performance are also going to improve non-hardware transaction performance. So now we add the TStruct, and now we're outperforming unordered containers on low thread counts, and we're continuing to scale kind of through what's reasonable for us to scale with hardware transactions. So all the way through to where we get to hyperthreads. So this is, I'm really excited about this work, and I think there's lots of interesting places to go continuing from on here. We've got a much better understanding of what the performance issues are, and we're getting good performance now, and HTM is really proving to be a very flexible tool that helps performance. And also as new machines come out, further hardware iterations on this, the hardware transactional memory support is going to get better too with newer machines as this becomes more pervasive. So I'm looking forward to continuing this research, and love to hear your questions and feedback. Thanks. Yeah, it's really that's a difficult aspect of kind of deciphering what's going on, and I've played with a lot of things. I have to say though, it's sort of inconclusive now. If I do things to make GC happen more frequently, sometimes that can be really beneficial, and that may be that the program is kind of getting stuck in a rut where it's always falling back to the software code path and not using the hardware transactions because the software fallback is conflicting with other hardware transactions. And then when I do a GC, I sort of kind of break the phase that we're in, and I can get back to running on hardware transactions. So that's not great. We should be managing that at a different level with our transactional memory system. So effects like that sort of mask the ability to really kind of pin down what the right settings are. Another thing that I played with is alignment. So if I change allocation for transactional memory structures, so the internally used ones and TVARs and my TStructs, and make them all cache aligned, I should, in theory, this should really benefit things, but it ends up increasing the memory footprint enough that I don't see the benefit. So if I find, the magic place in between, where I'm not increasing the memory footprint too much, but I'm getting a lot more aligned accesses, then, that should really give a boom. But as I was doing this work, running on Intel's emulator that emulates hardware transactions so I can kind of see what memory accesses are killing off transactions, it looked like a lot of the things that were being killed off were stack stores, which shouldn't be conflicts. And so fiddling with the stack size numbers made the stacks align slightly differently, and my guess is that we saw a lot less cache associativity overflows, and that drastically helped things. So just changing, I think the default is 1K stack sizes, changing it to 4K, all of a sudden things work better. So it's small little kind of details like that that I've fiddled with, but still haven't really found, the real root cause necessarily. But I think we're making a lot of progress. I think you have.
So, for completeness, there were a lot of different options on that graph, but for completeness, it would be really nice to have a raw CAS version of one solid. So, atomic modified IRF on a hash map is kind of a perverse option. People
Yeah.
very widely used.
Yeah.
It creates all this black hole.
Yep.
And just doing raw CAS and avoid that black hole. And we found this is just significantly better.
Yeah.
So let's go with it.
Right.
I was wondering, regarding black hole, in your threads code, event traces, or whatever, what was happening with black hole? Like, why are you getting false positives on the stack? Are those for normal stack pushes or for function updates?
So this is really sort of L1 performance, right? So it's just happened that all of these threads are doing the same thing, and we have a lot of them, and they all sort of kind of timed right, and their initial stack addresses all lined up to be the same cache entry, basically. So I have, say, a call will push the return address onto the stack. And that push ends up being the same distance away for all of these different stacks. And they all sort of, if they all call within each other's time frame, all of a sudden I've blown my L1 associativity. It only takes 8 writes to make a conflict.
False sharing is that they're in the same cache length. This is
Right.
different cache length.
Same associativity. Yeah. I think something that's really that I felt like I've heard from the community is use SDM for correctness first, and then if you run into a performance bottleneck, switch to something else. And this is telling a completely different story, right? Use SDM for performance, but it's only when you have a huge machine like I do. Hopefully other people are getting huge machines because they're terribly fun. And another aspect of that, I think there's a lot of ways the runtime system can be made better to deal with huge machines. One in particular that's crucial for this is pinning capabilities to threads. Linux does a bad job of allocating threads on this particular machine. And there's a lot more that can be done. On this machine, it really should be thought of as a non-uniform memory access machine. And so getting things aligned correctly is tricky, and we need to at least be able to express that so we can get the runtime system going there. So things like the I/O manager should really only be on certain cores because you want to be close to where you can actually do I/O. You can't do I/O from can't directly do I/O from every core on this machine.
So, did I hear you right? You said in the fine-grained version, you track not only the T-bars, but all writes to memory as part of the transaction?
The hardware transactional memory automatically does that.
So,
right.
does that mean that if I have a bug and update that,
Mm-hmm.
and then the transaction
Yep.
unrolls that?
Those updates can be conflicts, yeah. But we can still.
No, not conflict, but the update will be gone.
Yeah, right. The update would be gone if we fail. Yeah. Mm-hmm. But we can do better on that. And some future work that I want to do is push into the compiler the concept of, or libraries wherever, the concept of a read-only transaction, and keep that information as long as possible, and even delay writes to TVARs in transactions to the point where we have a longer sort of prefix to a transaction that if we find a problem, we can commit the hardware transaction to keep all of those thunk updates and still fail with a logical conflict from the transaction.
You mentioned that hardware is improving.
Yeah.
What do you see in particular? I mean, for example, will we be able to have hardware support where we say, I only want to track these, because we can track T-bars.
Right. Yeah, so So, yeah, there's a lot of talk in the transactional memory community of we would like to have the ability in a hardware transaction to access non-transactionally to memory. And IBM has some support for that, but it's really expensive. And it's tricky to get right. Intel has basically said, if you give us a really good use case for it, then we'll implement it. Well, right. So, but the costs are very complicated, like how to implement that and what sort of cost trade-offs there are. So it's tricky, but that's something down the road that we will see sort of creeping in. The implementation right now is very conservative because if you start to have these special features, you can get extremely crazy debugging situations where there's absolutely no way to figure out what's going wrong because the hardware transaction is very opaque. That's going to improve with the Skylake processors. They have this very exciting and interesting cheap way to profile branches. And those you can actually see inside hardware transactions in some circumstances, and that's great. But yeah, just in general, the implementation is improving in the sense that there are certain buffers and ways that it works that can be expanded and improved.